And for the students who are not attending the classes regularly, it will be very difficult for them to pass the subjects. This flexibility is given to you to attend the classes from your home. Teachers are available anytime. Okay, so you have to take the advantage of these things, and at the same time, you can prepare for your gate examinations also, because now this is third year. This third year is very important. When you will enter into your final year, lot many things will happen. Your major focus will be on your placement, okay, or your what you should do for your career. So this is the third year, and it is very crucial. Maybe from first semester of your final year, companies may call you for interview, okay, or some campus placement. Companies come for campus placement, so they will basically ask you the subjects what you have studied in your third year. Okay. So that's why I'm telling you this third year is very important. What are the subjects you are studying here? Like fluid mechanics, design subject is there. Maybe some thermodynamics you have studied in this semester or previous semester. Gautam?
Sir.
Thermal
Yes, sir.
subjects you have studied this year or previous year?
Previous year, sir.
Okay. So these subjects for any stream, suppose any company is there, okay. So either it will be from design, it will be from fluid mechanics, okay, fluid flow concepts, or it may be from thermal, or maybe from production. So as per your choice of interest, in which area you are interested, it can happen that some student is good at design, he is not good in manufacturing. Okay, it can happen that he is good in thermodynamics, but he is not comfortable with the design subjects, or maybe he is comfortable with this fluid flow, and it is a topic of interest for him. So you decide which is your area of interest and keep that one subject very strong. Okay, besides clearing all the subjects, you have to make one thing very strong. Okay, one subject, because if you appear for interview or any internship programs also, they will basically ask you which is your area of interest. Then you have to tell something. So by now only you start preparing. Okay, don't wait for those opportunities to come and then you will start preparing. Okay. So it's 25 in numbers and time is also 10:05. So we will start now. Impact of jet on vanes. Okay. So we have discussed in your lab session also, theory part I have already discussed. Still I will go through it, okay, because this topic is very scoring, interesting, and easy to understand. Okay. So before starting this unit, I would like to tell you what we are going to study in this unit. Okay, so it should be clear to all of you. On the screen, you can see one figure is there. Let me make it large. Yeah. On the screen, you can see one pipeline is there. Okay. This is your pipeline. A nozzle is connected to this pipeline. Now I hope it is clear to all of you what is the meaning of nozzle. Here you can see the cross-sectional area of your pipe is reducing. Okay, so if the cross-sectional area of pipe is reducing, the velocity will increase. Keep this in mind. Again and again I am repeating it. Okay, so what is the velocity over here? It will be slightly higher than what is velocity over this cross-section. Okay, this is the function of this nozzle. We want to increase the velocity of the fluid flow. Okay, so now you can see here the fluid is flowing.
Sir, the slide is not clear, sir.
Slide is not clear. Okay. Yeah, for me also it seems to be a little bit blur. Okay, don't worry, I will share then some other, where is that? Okay, now this is visible.
Yes,
I
sir.
hope this is okay.
Yes, sir, visible, clear.
Okay, okay. Now let me bring in those annotations here. Yeah. You can see here one pipeline is there, nozzle. So we are increasing the velocity of the fluid flow through this reduced cross section. And you can see here on the right hand side, one plate is connected. Okay. And this symbol, if you will focus on this symbol, this is representing that this plate is hold stationary. Okay. This plate is fixed. It is not moving. Okay. This symbol, you keep in mind. Why I am telling this? Because first case we are studying where the plates will be in stationary position. Next case we will study when this plate will also be moving. Okay, this plate will also be moving. Now what is happening here? The fluid is coming. Let me see whether I can change the color. Yeah, I can change the color also. Yeah, you can see here. Blue color I am using. Okay, the fluid is flowing in this direction. The fluid is flowing and it is giving an impact on this horizontal plate. Okay, and afterwards those fluid is moving in perpendicular directions in both the sides, upside and downstream side, both sides. You can see the fluid is moving. We are assuming here that there is no frictional loss, and another assumption is there is no loss due to the impact of this jet. Okay, so if there is no loss in kinetic energy, then the velocity at this location will remain the same at this location also. Okay, so since there is no loss of energy due to that impact, so the velocity will remain the same. There is no frictional losses also. Okay, so these things you have to keep in your mind. So when the fluid is impacting or hitting this plate, one force will be exerted by this flowing fluid on this fixed plate. So we have to calculate how much force that fluid will exert on this plate. This is as simple as what I'm telling you. Okay, some fluid is hitting a fixed plate. So what force that fluid is exerting on this fixed plate, that we are going to calculate. So this is the force exerted by jet on a vertical plate. Now, here you can see the plate is exactly vertical. The plate is exactly at an angle of 90 degrees. Okay, this angle is 90 degrees. It means the plate is exactly in vertical position to the direction of fluid flow. Okay, in next case, what we will see, uh, it will be inclined at some angle. This will be the inclination. Suppose it will be inclined with some theta angle. This will be some theta. Then what will happen? So the first case, when the plate is held stationary vertical. Second case, when the plate is having some inclination. Third case, we will see when the plate is curved in nature. Okay. So one by one, we will see them all together. Let me see whether they are here. If it is there, then I will show you. Yeah, this is for your inclined plate. What will happen when the plate is inclined? How much this fluid will exert the force on this inclined plate? Okay, but still, what you can observe here, still the plate is fixed here. Okay, so this will be our second case. And after this, the third case that we will see is this one, where the plate is curved. Okay, and it is fixed. The plate is fixed and curved in nature. Now it is not straight. So what will happen when the fluid is hitting here at the center? Okay, and the fluid is exiting tangentially with this curved plate. Okay, so now you can see the velocities, exit velocity is making some angle theta. So we will break the components sine theta and cos theta. We will see one by one. So I have shown you just all the three cases what we are going to study. Now we will see the mathematical part. As we have studied or discussed earlier also, that we will be using Newton's second law of motion for its mathematical derivation. Okay, now let's see what is the introduction written over here. When the liquid comes out in the form of jet from the outlet of a nozzle, which is fitted to the pipe through which the liquid is flowing under pressure. As I have told you, the liquid is flowing under pressure at this location. If some plate which is fixed or moving, okay, the plate which is fixed or moving, let me change the thickness of this. In the path of the jet, force exerted by the jet on the plate, we have to calculate. And how we will calculate it? This force is obtained from Newton's second law of motion. Keep this in your mind. Okay, Newton's second law of motion. Or we have discussed earlier also impulse momentum equation. Impulse momentum equation. Okay. Thus, the impact of jet means force exerted by the jet on the plate, which may be stationary or moving. Okay, this plate may be stationary, may be moving. Okay, so we will see two cases. The first case here you can see where the plate is stationary. The second case where the plate is moving. Plate is vertical, plate is inclined, plate is curved. Okay, for the second case, the plate will be moving. Okay, those three cases only, but this time it is not stationary, it will be moving. Now, let's see the derivation part. The velocity of jet is represented by your capital V. Okay, the diameter of jet, it will be represented by this location. This is your diameter of the jet. Okay, represented by your capital D. The small d, diameter of the jet. A will be the cross-sectional area of the jet. We all know the formula for the cross-sectional area will be pi by 4 into d square. Okay. Now, if you remember the impulse momentum equation that we have studied, okay, when the jet will strike the plate, jet after striking the plate will move along the plate, but the plate is at right angle to the jet. Hence, the jet will be deflected to 90 degrees, as I have told you earlier. Okay, here I have told you that two assumptions we are taking. First, there is no frictional loss, and the second one, there is no loss of energy due to the impact of those fluids on the plate. Okay, now as per your Newton's second law, okay, or impulse momentum equation, we know that force exerted in the direction of the jet equals to rate of change of momentum in the direction of force. Rate of change of momentum in the direction of force. Now, rate of change of momentum means initial momentum minus final momentum. Now, what is momentum? Momentum is nothing but the product of your mass into velocity. Okay. So, if I am telling initial momentum, then mass flow rate will remain the same. What is changing? Velocity. Okay. So, we can say mass into initial velocity minus mass into final velocity upon time. Okay. So, as I have told you, this mass flow rate will remain the same. So, we can take this mass upon time outside of the bracket. What will remain inside will be your initial velocity minus final velocity. Initial velocity means velocity of the jet before striking and velocity of the jet after striking. Okay, from the previous diagram, velocity of the jet just before striking the plate and the velocity of the jet when you have struck it and you are moving away from it. Okay, so these are the initial velocity and final velocity. Okay, stay focused, because if you understand the concept, how we are deriving it here, this entire chapter will be very easy for you. Okay, and you can easily solve all the numericals if you understand this step. This I am highlighting. if you understand this step, that force in the direction of x, why I have written x? Because x is your horizontal axis we are considering, and the jet is moving in your horizontal direction. So it means the force that we are calculating, okay, the force is in also in the direction of flow of your fluid direction. Okay, so it is given by mass flow rate, mass per second, here it is written, you can see, into initial velocity minus final velocity. What is the mathematical expression for mass flow rate? Keep this in your mind. Rho into A into V, where rho will be the density of the fluid, A is the cross-sectional area, and capital V is the velocity of the fluid. Okay, we all know that velocity of the jet before striking is given by capital V. Okay, now final velocity, here I am writing 0. Can anyone tell me why I have written here 0?
When the water strike on the blades, then the velocity becomes 0, sir.
Not complete answer. Answer is correct, but it is not complete. See the figure, then you will get some idea. Yeah, here. Here I am telling you that we are calculating the force in the direction of fluid flow. Okay, and what is the direction of fluid flow? Horizontal direction. Okay, so here at this location, the velocity is v. Okay, now final velocity I told at the exit location here. And you can see here velocity is v here also. But the thing is, it is in vertical direction. Okay, and we are calculating the force in the direction of fluid flow in this direction. So what is the component of velocity in x direction? It is 0. We have only y component velocity here. Okay, so that's why we have taken final velocity as 0. Okay, I hope it is clear to all of you. So that's why we have taken final velocity as 0. Now, if you will multiply this, this is a simple expression that you are getting rho into A into V square. Okay, so this is the expression that you have to use for solving the numericals. Okay, when the plate is stationary and some fluid is hitting it with velocity v, okay, with velocity v, the nozzle cross-sectional area is small a and the density of that fluid is given by rho. So this is the derivation part of the force exerted by the fluid on flat vertical stationary plate. I hope it is clear to all of you. If it is clear, type in the chat box, clear sir. If you have any doubt, you ask me, I will clarify it. Yes, one student has written clear sir, waiting for others response. Now we have 48 participants and only 2, 3, 4. Now clear sir is coming. Yes, you have to respond like this. Okay, very good. Yeah. Then I will came to know how many of you are actively listening and how many of you have just started the meeting to show your presence. Still the number is increasing. Well, good. If you have any doubt, feel free. Okay, don't bear any pressure. If you have doubt, I will clarify it. Because if you understand this concept, you will be able to solve entire numerical of this chapter. What is the concept? Takeaway point, I will say. Takeaway point is force we are calculating in the direction of fluid flow. Keep this in mind. Okay, force we are calculating, but it is in the direction of fluid flow, Fx. Okay, in later on cases, we may change this. Okay, so force we are calculating in the direction of fluid flow, which is given by initial momentum minus final momentum, rate of change of final moment, initial momentum and final momentum. Okay, so we all know that momentum is nothing but mass into velocity. So initial velocity minus final velocity. So simple expression is there, rho a v square. Got it? Now we will see the next topic. Now, what I have done here, we are going to study force exerted by the jet on stationary inclined flat plate. Here you can see the plate is making some angle. Here the plate is making some angle theta with the direction of your fluid flow. In this situation, what we will do? Okay. So we are going to calculate here the force perpendicular to your plate. Okay, the plate orientation is like this. How much force this fluid will exert on this plate in normal direction, and then after that we can break it into component. Okay, that is your x component or your y component in whatever the direction you are looking for. Okay, so let's see here. We all know that mass flow rate of the water striking is rho into a into v. Okay, velocity of the fluid is given by capital V. Angle between the jet and the plate is theta. Okay, so now we will see its mathematical part. Now, see here that those 2 points are highlighted here. What are those 2 points? The first point, the plate is smooth. What this term is saying, if the plate is smooth, means there is no friction at all. Okay. And the second assumption is, if it is assumed that there is no loss of energy due to impact of the jet. Okay, the two assumptions. The first one is your plate is smooth. The second one is your loss of energy due to impact of the jet is negligible, or no loss is occurring there. Then the jet will move over the plate after striking with the velocity equal to the initial velocity. Then only if these two assumptions will act, then only the final velocity and initial velocity will remain the same. Only thing is direction you have to keep in your mind. Okay, so let's see how to find the force exerted by the jet on the plate in the direction normal to the plate. Okay, I have shown you that Fn, the direction normal to the plate. Okay, formula will remain the same. Here we are using this Fn term, okay, because we are calculating the normal force. Normal force means perpendicular to the direction of the plate. Now, mass of jet striking per second, mass of jet striking per second is nothing but your mass flow rate, that is given by rho into a into v. Okay, and initial velocity before the jet will strike the plate, and final velocity, okay, initial velocity of the jet before striking the plate and final velocity of the jet after striking the plate. This we have to see. So again, I will show you that figure, and we will find out how to calculate the velocity before striking and velocity after striking. Okay. Yeah, here. Before striking the plate, here you can see the velocity we are taking. This is, if this is your V component, if this is your V component, this angle is theta. This angle is theta. Okay. So what will be this angle? 90 minus theta. Okay. So the component of velocity in normal direction to this plate, it will become sine theta, V sine theta. Okay. This is the velocity component normal to your plate. After striking the plate, what is the velocity you are getting here? This is your V. Okay. And we are looking in this direction. Do you have any velocity in this direction? No. Your answer will be probably no, because the velocity, the fluid is going in this direction only. And we are eager to calculate the force in normal direction. So in this direction, there is no velocity component. Okay. So that's why the final velocity term will be 0 and initial velocity term will be your v sine theta. Rest all remain the same. Okay. So let's see here. So this is how they have written that Fn equals to rho into A into V. Okay. This is your mass flow rate. Initial velocity v sine theta. How it comes, I have shown you through the diagram. Final velocity 0. Okay. The thing that you have to keep in mind is the direction. We are calculating both in the direction of n. So if you will simplify it, what you will get? Rho A V square into sine theta. This is your expression for the force, okay, in normal direction. Now, you can break this component into vertical as well as horizontal direction. So it is resolved into two components. First one is your Fx, second one is your Fy. Okay. So one direction in the direction of the jet and another perpendicular to the direction of the flow. Okay, since it is at some angle, so there will be two components. Now see here how it will come again for this Fx, how it is equals to Fn cos 90 minus theta. You have to see that diagram. I will take you to that diagram. Yeah, you have this Fn in this direction. Fn is there. Okay, in this direction you have Fx. So you have to see what angle it is making. 90 minus theta is this one. So your Fx will be nothing but Fn cos 90 minus theta. Okay. Similarly, if you want to calculate this one, it will be Fn sin 90 minus theta. Okay. So this is how that component has been broken. Okay. Someone has written clear, sir. That is good. So this is how we calculate the components. So Fn cos 90 minus theta. Later on, for cos 90 minus theta, you can write sin theta. And for sin 90 minus theta, you can write cos theta. Okay. So what expression you will get? Fn that you have obtained over here, that is rho A V square sin theta, into this sin theta will come. So it will become rho A V square sin square theta. This is the force component in x direction. Okay. Similarly, you can calculate force component in y direction. So sin 90 minus theta will become cos theta, and the final expression that you will get is rho A V square sin theta into cos theta. So these are the expressions that we have obtained for Fn, Fx, and Fy. Now the third one that I have told you, when the plate is in curved position, when that plate is curved in nature. So here you can see plate is fixed. How you can show the plate is fixed? This diagram, this notations you have to use. This I am highlighting, circling, because in examination, many of the students forget to draw this. Okay. So that's why I am telling you that do not forget this. If you have to represent that the plate is stationary, you have to draw this symbol. If you will not draw this, then I will think, or examiner will think, that the plate is moving with some velocity. Okay. Now let's see. Let the water jet strikes the fixed curved plate at the center. Here we are hitting this curved plate at the center of this curved plate, and you can see it is symmetrical in nature about this center line. Okay, about the center line it is symmetrical on the both sides. Okay, those two assumptions will stay here also. What are those two assumptions? The plate is smooth and there is no loss of energy due to impact of jet. These two assumptions always keep in your mind. When the plate is hitting and there is no friction, then definitely what it will do, it will move tangential direction to your plate. And what is that tangential direction? This is your tangential direction. So, and since there is no loss of energy, the velocity will remain the same in tangential direction. It will be given by your V. Okay. And it is making some angle theta. You can see here, it is making an angle theta with your horizontal direction. Okay. So horizontal component and vertical component you can break here. That is nothing but your V cos theta and V sin theta. Okay. Now, one thing that you can keep in your mind here is the direction of flow here. What is the direction of flow here? You can see at this location, the fluid is moving in positive X direction. I'm talking about here for X direction, means horizontal direction. And if we are looking the horizontal component over here, it is moving in negative X direction. It means they are opposite in direction. Okay. So the component of velocity in the direction of jet, we have to take minus V cos theta. Okay. So I have given the explanation why we are taking this negative sign. We are taking this negative sign because they are in opposite direction. The flow of direction is opposite to each other. Okay. This is here written, negative sign is taken as the velocity at the outlet is in opposite direction of the jet of water coming out from the nozzle. Okay. Now we will see the mathematical part. Okay. So for your clarity, I would like to tell here once again how we are calculating that mathematical expression. That same formula you have to use here also. Mass flow rate into initial velocity minus final velocity. Only thing that you have to take care is your direction of the fluid flow. Okay. So let's see. Yeah. First, we will calculate in your X direction. Force exerted by the jet in the direction of the jet. In the numerical, it will not be written in X direction or Y direction. They will write in the direction of jet, perpendicular to the direction of jet. So if it is written in the direction of jet, you have to take care. For this case, for this particular case, it will be Fx. Mass per second, it is mass flow rate into V1x. What is here V1x? At this location, I am taking it as 1. At this location, I am taking it as 2. Location number 1, before striking the plate. Location number 2, after striking the plate. Suffix x is coming because we are taking in X direction here for this case. Suffix x. So V1x means velocity at point 1 in the direction of X. Okay. V2x means velocity at point 2 in the direction of X. Okay. So we know that at point 1 it is V, at point 2 it is minus V cos theta. Okay. So you can substitute this value. You know the expression for mass flow rate. It will be rho into A into V into V1x minus V2x. Let's see afterwards what is happening. Yeah. So here you can see rho AB V minus of minus V cos theta. So minus and minus, it will become plus. Okay. So what you are getting here, rho AB square into 1 plus cos theta. So what is the final expression? This is your final expression for force in X direction. Okay. And what is that? It is nothing but rho AB square into 1 plus cos theta. So you have to keep this in your mind. Rho AB square 1 plus cos theta. Similarly, in Y direction, now we will calculate, that is your Fy. Fy we are going to calculate. The formula will remain same. Mass flow rate into V1y minus V2y. Now, try to think, try to assimilate what is this V1y. V1 means velocity at point 1 in Y direction. Velocity, this term, what it is saying? velocity at point 2 in y direction. Okay, so once again I will take you to that diagram. Now this diagram, if you will see, what is the component of velocity in x direction, y direction here? In y direction, the velocity component here is 0. Okay, and at location number 2, the velocity y component is v sine theta. Okay, so this you have to use in your numerical expression. So initial velocity we are taking 0, final velocity we are taking v sine theta. Okay, why here we have not taken minus sign? Because this v sine theta in vertically upward direction. Okay, so what expression you will get here? You will get here minus rho a v square sine theta. Okay, here the negative sign, what it is representing? It is representing that the force is acting in downward direction. Okay, and the angle of deflection of the jet, this you have to keep in your mind, because in numericals we will be using this term, the angle of deflection of the jet. In numerical, this data will be given, angle of deflection of the jet. So this is 180 minus theta degree. Okay, how it is coming like that? Suppose this is that same figure you can see here. If you are extending this on the back side, I am extending this. It is intersecting at this location to the horizontal axis. You can see here on the downward side, and this angle is your theta. This is your theta angle. So what will be this angle? This will be your 180 degree minus theta. So this angle is normally called as the angle of deflection. Why? Because the fluid is coming in this direction and it is getting deflected in this direction. Okay, so that's why this is your angle of deflection. In numerical, they will use this term. The angle of deflection of the jet is given by some angle will be given. So you have to calculate like this. Okay, so we have seen 3 cases. The first one is your when the plate is stationary vertical. Okay, second case when the plate is stationary but it is inclined at some angle. Okay, and the third case we have seen when the plate is curved and it is stationary. 3 cases we have seen. Its mathematical derivation we have seen. Now one numerical from all the 3 cases we will solve. Okay, so I'll go again back to my PowerPoint slide and we will solve numerical. And I'm expecting all of you to be ready with your calculator now. Okay, all of you be ready with your calculator. Now we will solve numerical and do fast calculation, because we have now 10 minutes. In 10 minutes, we have to solve 3 numericals. Okay, one more case is there when the curved plate is striking tangentially. Okay, so let's finish this, and numerical we will solve in next class, tomorrow's class. Okay, so for clear visibility, again I will go to that PDF version. Okay, yeah, this is the 4th case. I'll try to bring this at the center because we know what are the steps to be followed for its derivation. So I'll focus on this diagram only. If you learn how to draw these velocity diagrams, this is basically called as velocity diagram. Keep this in your mind. Okay, velocity diagram. If you know how to draw this, how to draw the different velocity and force components, then you can solve any numerical. Okay, so you can see here the fluid is now coming in this direction. It is entering inside this curved plate tangential to it. Okay, it is entering tangential to it. Okay, now if it is entering tangentially, then you can see here this is your velocity v. Okay, so its horizontal component will be v cos theta and your vertical component will be v sin theta. Okay, it is, since it is making an angle theta with the horizontal. So here, what will be your V1x? Yes, anyone in the class? V1x that we are using in that previous formula.
V cos theta.
Yes, velocity at point 1 in x direction. Now velocity at point 1 in y direction, V1y.
Sin theta. V sin theta.
Yes. Now come to your exit location. Means point number 2. This is your point number 2. V2x. What will be V2x? Yes.
Minus V cos theta.
Yes, minus V cos theta, because it is going in opposite direction. Okay. Similarly, what will be V2y? It will be V sin theta. Okay. So direction here you keep in your mind. Now, if you understand this velocity diagram, okay, how to draw this, then you can easily do all the calculations. Now, velocity drawing is important. If you have drawn that velocity diagram perfectly, then it will be perfect calculation. This chapter is a scoring chapter. Again and again, I am telling you. Okay. So those two assumptions will stay here also. What are those two assumptions? One again, plate is smooth and loss of energy due to impact is 0. Keep these 2 points in your mind. For every derivations that we are doing now, these two assumptions are common to all the derivations. Plate is smooth means frictionless. Loss of energy due to impact is 0. For this case, if we are considering these two assumptions, then what will happen? The velocity at inlet, that is represented here by V, will remain the same at inlet as well as outlet. Okay. If there will be certain losses in this, there will be some friction, then this V will change. Okay. So that's why we are assuming here that the plate is smooth and there is no loss of energy. So the plate at the inlet velocity as well as outlet velocity will remain equals to capital V. Now, again coming to your x direction, we will calculate force in x direction, Fx, and force in y direction represented by Fy. Okay. So Fx will be mass flow rate into V1x minus V2x. Okay. So mass flow rate is given by rho into A into V. V1x we have seen here, it is coming V cos theta. So we have written V cos theta. V2x we have seen here, it is in opposite direction. So we are taking it minus V cos theta. So minus and minus, it will become plus. And what you will get, 2 V cos theta you will get here, and 1 V is outside. So final expression that you will get is Fx equals to 2 into rho into A into V square cos theta. Okay. I hope it is clear to all of you. Now, similarly, you can calculate in y direction also. Okay. So how to calculate in y direction? See, I have to bring in one screen. Yeah, here. Again, the formula will remain the same. Rho into A into V into V1y minus V2y. Now, what is V1y? V sin theta. What is V2y? It is here. V sin theta again. Okay. Directions are same. So you can write V sin theta minus V sin theta. So it will become 0. Okay. So force in y direction here, you are getting Fy equals to the magnitude of this Fy force will be equals to 0. Only what you will get? V force in x direction, that is represented by this Fx. And what is the magnitude of that? It will be 2 into rho into A into V square cos theta. So this is the fourth case we have seen. Okay. Flat plate is stationary, inclined plate is stationary, curved plate hitting the jet at the center line, curved plate, the jet is entering tangentially to the plate. Okay. So now I would like to ask, if you have any doubt in these what we have discussed today, you can ask me all the 4 cases. Now the session is open to all of you. Or if it is clear, then you can write clear, sir. If you have any doubt, you ask me. I am sitting here to clarify your doubt. This is the theory part that we have taken today. Tomorrow we will be solving numerical. Okay. So I expect all the students to be ready with your calculator. Okay. And some student is writing, sir, please go slow. How slow? How much slow? I am thinking that I am going very slow. If you have doubt in any understanding of any concept, you ask me. I'll clarify it. I think in first week or second week of January, your semester is going to end. Okay, 10th of January. So we have to finish the syllabus before that. Okay, and this topic, what I have taught today, I feel that I am discussing this topic third time. Once I have discussed when I was taking your lab session. Okay. Second, again in the lab, I have given you one overview. That time also I have discussed, and this also. So I think you need to update your speed. Okay. You have to pace up. The world is moving very fast. If you will go slow, you will be staying on the backside. Okay. So if you have any doubt, you ask me. I'll clarify it. Okay. But the role of any coach, the role of a teacher, the role of a mentor is to guide your students, to make them up to the pace of the what time is demanding. Okay. So don't worry. If you have any doubt, I will clarify it, but don't ask me to slow down now. Okay. I hope it is clear to all of you. And we will meet again tomorrow.
Sir, these numericals of just strike the curved plate at one end tangentially when the plate is unsymmetrical.
Yeah.
Based on this also we will get numerical, sir.
Yes, yes. Based on that also. But I have not taken that topic now because we are almost 10:50. Okay. So I think we will discuss it in some other class. Okay, tomorrow's class.
Okay.
So 4 cases we have seen today: when the plate is stationary, flat plate; when the plate is stationary, inclined plate; when the plate is curved and the jet is hitting at the center line; and the 4th case is plate is curved, stationary, and the plate jet is coming tangentially to your curved plate. Okay, with these words, I'm going to end today's lecture. We will see you tomorrow. Okay, and get ready for solving the numericals. Try and prepare your own notes today only, so that you will be doing competition with yourself. That if you are taking 2 minutes to solve this numerical, now you have to compete yourself that you will solve it within 1.5 minutes. Okay, don't compete with others, compete with yourself. Okay, then something new will come out of you. Okay, I'm going to end the meeting.